Welcome back, dear students. We'll solve problems on temperature stresses. Let us consider this problem. You write down, just I state here and pause the videos and start writing. A composite bar is rigidly fitted at the support A and B as shown in the figure. Determine reactions at the supports when the temperature rises by 20 degrees centigrade. Take Young's modulus A as 70 giganewton per meter square and Young's modulus S is 200 giganewton per meter square, and they have given also alpha A as 11 into 10 raised to minus 6 per degree centigrade. Then alpha S is equal to 12 into 10 raised to minus 6 per degree centigrade. Okay, and the figure given is this way. This is a one bar and another bar is attached to that. Okay, and this bar is fixed here and this bar is fixed here, and this is made up of steel and this is made up of aluminum, and it is 1 meter length and this is 3 meter length. Okay, and its area is 300 mm square and its area is 600 mm square. Right, this problem it is given. They are saying that the temperature is earlier something and later 20 degrees increased, means I can get that delta T change in temperature is 20 degrees centigrade. When 20 degrees centigrade is increased, then obviously this bar will expand, but this expansion is restricted by the support. When this is restricted, then how much force induced inside, that we need to calculate. Okay, or otherwise how much stress induced in the bar, that also you can calculate. Okay, now we'll go to solve this problem. Look at here. Let us think that there is no restriction. When there is no restriction means this is removed. When this is removed, because of the increase in temperature, this will expand its distance. But actually speaking, this also expands, means this bar pushes this one, therefore it comes here, and this is also expands. Therefore, total expansion is equal to expansion in the aluminum plus expansion in the steel due to temperature, because we are not pulling it due to temperature. Therefore, L alpha T of aluminum plus L alpha T of steel. L is 1000 mm, alpha is 11 into 10 raised to 6 minus 6, T is a 20 degrees centigrade, plus L is the 3000 mm into alpha is a 12 into 10 raised to minus 6, then T is a 20 degrees centigrade. This answer is 0.94 mm. 0.94 mm I got. This is when we assume that there is no restriction. Okay, now what? let us consider there is a restriction. That restriction is like we are pushing it back. We are using some force P and pushing this back to its original position, pushing this back to its original position. To do that one, that how much I need to push? I need to push this pushing means external force is coming now. Total total amount of total amount of deformation need to push need to push push back by P load equal to, what is that, PALA by EALA plus PSLS divided by ASES. Sorry. AAEA, AAEA and ASES. This much I need to push it back. But here the one thing tricky is given here is the unit of EA. Unit of EA is 70 giganewton per meter square. Giganewton per meter square means this is a PA, this is a GPA. GPA to MPA just simply into 10 raised to 3. Then it becomes MPA. Okay now? Like that, EA it is like ES equal to 200 GPA, 200 into 10 raised to 3 MPA. How it is converted? You watch the first lecture of strength of material, first or second lecture. There I explained how conversion of these units. Then I know everything. I will substitute here instead of P. Now see this P and PS. Go back to the figure. Whatever the P you are pushing here, the same P will push this also. Therefore P for aluminum, P for steel, both are same. Therefore I will take P outside common. Inside LA, aluminum is 1000 divided by, and area is 600 mm square. Then aluminum 70 into 10 raised to 3 plus PS length is 3000 divided by area of steel is 300 mm square into 200 into 10 raised to 3, and this is nothing but your delta, that is 0.94. From this simplification I will get a P equal to 12735.4 kilonewton. Means this much force is required to maintain it in the fixed position if it freely expanded by the temperature. Okay. Next,